Now we have the question, if the Laplace transform of a function is 3 over s squared, then what is the function? Well, last time we saw that the Laplace transform of the function f of t equals t is 1 over s squared. Well, then it makes a certain amount of sense that we would maybe hope that the Laplace transform of 3t would be 3 over s squared, because we got 3 over s squared here. In other words, this is 3 times this, so we expect our function here will be 3 times what our function here is, and that's the way it works out. And it's really pretty easy to understand why. It's because constants come out of integrals and they come out of derivatives. So the integral of a constant times a function is just a constant times the integral of the function. So if you did the integral of 3t, it would come out exactly the same, the Laplace transform integral e to the negative st times the quantity 3t dt. You bring that 3 out, and it would just be 3 times the Laplace transform of t. You could write that out if you wish. I believe your book addresses it to some extent, and maybe proves it a little more formally than that. But we can get away with this, okay? The Laplace transform, in summary, is a linear operator. The Laplace transform of constant times a function is that constant multiplied by the transform. And the transform of the sum of two functions, because the integral of a sum of two functions is the sum of the integrals, the Laplace transform of the sum of two functions will be the sum of the Laplace transforms, and vice versa if you work backwards. So, now the way we're going to write this, if the Laplace transform of f of t is 3 over s squared, we're going to conclude then that f of t is 3t. Okay? And we're going to call that the inverse Laplace transform. Okay? The inverse Laplace transform of 1 over s squared is t. Because why? Because the Laplace transform of t is 1 over s squared. There's a one-to-one relationship between functions and their Laplace transforms. And this goes back to what I said. When you do the Laplace transform, you don't lose any information. Okay? So you have if you've got the Laplace transform, there's a unique function that goes with it. If you've got the function, there's a unique Laplace transform that goes with it. Okay, well, it follows from linearity that if the inverse Laplace transform of 1 over s squared is t, the inverse Laplace transform of t over s squared is 3t. Now we also, and we talked about how you could recursively prove or inductively prove this formula, okay? Laplace transform t to the n is n factorial over s to the n plus 1. In a very similar manner, if you just write down the integral and keep integrating, you'll obtain that function. Okay. And actually, okay, never mind. Okay, now, if the Laplace transform is 2 over s minus pi, then what's your function? Okay. Well, here's where we have the table. We can use the table. We can understand very easily. We've already done the integrals for, a good number of the things in that table. We've done integrals for sine. We've done integrals for cosine. We've done integrals for t to the n. We've done an integral for the Heaviside function. And we've seen how the Laplace transforms of derivatives work out. I'm just pausing because I'm kind of almost getting confused about the order we did things in class, because I'm doing the videos in a little bit out of order just because of where the boards were sitting. So ignore that. Okay, we're trying to do the Laplace transform of 2 over s minus lambda. We obtained, or we will obtain, and I'm trying to look to see if we've done that, the shift rule. And I'm pretty sure we did that with the Heaviside function. Okay. 1 over s is the integral of the Heaviside function, and I'm treating it like it's the integral of the exponential function. So I'm going to stop here for a minute and make sure that I've got my head straight on this. As I say, the day we did this, I was in the midst of 36 hours of probably weather-related confusion coming from the fact that my body didn't feel great. So I was doing a lot of really ignorant things. So I might have done something pretty ignorant here. So I'm going to back up. I mean, all I've got to do is, okay, well, the integral of e to the alpha t, yeah, we did this, e to the negative st dt is 1 over alpha minus s times and from 0 to infinity. It turns out to be negative 1 over alpha minus s, which is 1 over s minus alpha. So I'm right here. Okay. So it's handy to understand the definition and understand how to work these things out. Sometimes you get yourself a little confused and you can write the thing out and there it is. And I should be able to do that in my head, but it's getting a little late. Okay, so I'm right here. I'm trying to okay, now I've got to think through the Heaviside function, but I'm not going to do that right now. Okay, so here we have Laplace transform of f of t is this, and this is just a 1 over s minus alpha, meaning, well, the Laplace transform, 1 over s minus alpha is a Laplace transform of e to the alpha t. Now alpha is equal to pi, so this is a Laplace transform of e to the pi t. And we factored the 2 out. Why did we factor the 2 out? Because this is in our table. Okay, now if we wanted to look at the table, we wouldn't have to think through this, but this is so easy to think through that I recommend you understand it well enough to do that. And hopefully more quickly and clearly than I can at this particular moment today. Okay, this is on the table. For the function e to the alpha t. Now, of course, in the table it's s minus alpha, so you got to recognize that alpha is pi. But that's all you have to do, and then you know that this is a Laplace transform e to the alpha t. That's what you write down, and you got your factor 2. The thing is linear, so that's completely justified. Okay. Then we had e to the 3t times 3 over s minus pi over 2. That was, I think, something about number 13 on the document. And we bypassed this one because we weren't ready to deal with this. And instead, I substituted the function, the Laplace transform s plus 1 over s squared plus pi squared over 4. Now, I asked people, what can you do with this? And, you know, people were apparently about as adept as I was that day, because everybody just kind of stared at me. But isn't it obvious, if you got s plus 1 over something, you can write that as s over something plus 1 over something. Well, everybody knows that. And if everybody knew that that would be a good thing to do, they would have told me that. So I'm not concerned about that. I think people were just feeding off of my lack of acuity. Okay, anyhow, yeah, that was easy. Okay, we do this, and now we recognize that there is a function in the table. And we just go to the table that corresponds to this, and that function is cosine of alpha t goes with s over s squared plus alpha squared, and actually I think your book has it in terms of omega, which is very appropriate because that's angular frequency, and when we're doing differential equations, if we have a cosine of a multiple of t, it's usually because there's an angular frequency omega. Okay, so this is in the table. So we can recognize this as an instance of what's on the table. Okay? Now, there's another thing on the table that fits this one. And that is 1 over s squared plus omega squared. So we look at the table and we find something that's of this form. And we see that that's this one, 1 over s squared plus omega squared. In both cases, omega squared is pi squared over 4, so omega is pi over 2. Then we just figure out our constants, okay? This is just straightforward cosine of pi over 2t. I wrote alpha here instead of omega, but you can think omega if you like. This is cosine of omega t, close the parentheses, for omega equals pi over 2. So this is a cosine of omega t. This one is, I'm not sure, oh yeah. Okay, what's in the table is not this. What's in the table is omega over s squared plus omega squared, not 1 over s squared plus omega squared. Okay? So omega over s squared plus omega squared would be the sine of omega t, but we don't have our omega up here. Our omega is pi over 2, so it follows, and you can think about this a little bit, that this is 2 over pi times the Laplace transform of the sine of alpha t, with alpha equal to pi over 2. Okay, now I might write that out again, just in a very short video, but that's the way it works.